Welcome to the tutorial question for supplementary on Emag, question 7a. So question 7a says, a smaller coil lies inside a larger coil, which is fixed in position. The smaller coil is free to move. The coils are concentric, horizontal, and carry current in the same sense, in the same direction. Will the smaller coil experience a resultant force? Will experience a resultant torque? So first thing is that we know if we have two wires carrying current in the same direction, they will experience a force attracting each other. Now, if we were to continue drawing, or if we were to imagine that we can continue drawing wires this way, it will still experience a force in attracting each other. So the same idea can be applied to circles, which is essentially made up of many small segments of wires that are parallel to each other. So you can imagine that there's a force like this for this segment, a force like this between these two segments, etc., etc. And these two forces are always equal and opposite in direction. And because this is a circle, the net forces for the red arrows acting on the inner circle, right? The net forces acting on this inner circle is symmetric in nature and hence must add up to be 0. Next, will there be a resultant torque? Well, again, there will not be, because the forces are pulling outwards on the circle. It is not a turning force. It doesn't turn the circle, because imagine the center of the circle. Center of mass is here. All of the forces, right, pass through this CG. Right, the line of action of force pass through this center of mass. Hence, there will be no torque. And even if they do not pass through the center of mass, because the forces are symmetric, the chances are that there will still be no resultant torque. Okay. So that's it for 7a. Let's look at 7b now. The current in the smaller coil is now reversed. Oh, that's interesting. Coil P has 10 turns of radius 4 cm and carries a current of 1 ampere. Coil Q has 20 turns and a radius of 12 cm. And the current is adjusted in magnitude so that the resultant field at the common center is 0. Find the current in Q. Right, so here we know that the central coil here, the current has changed direction. Okay, so using your right hand grip rule, right, we can tell that the B field due to this current must be pointing out the page in the middle. Right, so denoted by red. The outer coil has a current this way. So using your right hand grip rule, it has a B field pointing in to the page. Okay. So we can write that the two B fields, B total, equals to 0, 0. And this is due to the B due to the outer coil plus the B due to the inner coil equals to 0. Okay. Right, so what's next? Let's look at first the inner coil. How can we change this number? Right, so using this equation, right, mu naught equals to n. And for the inner coil has 10 turns. I is 1. Radius is 4 cm, so 0.04. The outer coil has mu naught. Now, they now point in different directions, right, the current. So one of them has to be positive and one of them has to be negative. So we just take the one that point out to be positive, which means the one is of the outer coil must be negative enough. Right, so this is just a convention that we use. Number of coils for the outer coil is 20. The current is what we're trying to find, I. To the radius is 12, so 0.2. And this whole thing is 0. So mu and mu cancels away, we don't need that. 2 and 2 cancels away, we don't need that. 20 and 10 becomes 2 and 1. Then 0.12 and 0.04 becomes 3 and 1. So we can actually solve for the value of the current being like this. So this is negative 2 over 3 I plus 1. So it seems that the current is 3 over 2. Oh yeah, and that's correct. So I, without any calculator, I equals to 1.5. Which is the answer that we have seen. Okay. Part C, the smaller coil is now replaced by a vertical wire carrying current into the paper. Will the wire experience any force? Well, this is slightly simpler, right? If you look at the current here, using your right hand grip rule, the B field goes into the page. Notice that the B field is denoted with a cross, while the current is denoted by a circle and a cross. Right, so if you have a B field going into the page and you have a current going into the page, they are in fact parallel. So no force experienced. Okay, no force experienced. Now let's look at the suggested solutions for A, B, and see if we made any strange mistakes. So part A, they are traveling in the same direction, so part B, same method, and then part C, no force, right? We are exactly